Okay, let's get started. Qiang, are you ready?
Yeah.
Okay. Well, it's a great pleasure to introduce Qiang. He's, as you all know, he's one of our own faculty, and I'll just mention that the new version of Stable Diffusion 3.0 just came out, and they heavily use rectified flow. It's something that both Qiang and Qiang Liu have worked on a lot. So that's super exciting to see that happening. So congrats on that. But this is also really excellent work. So take it away.
Thank you. Yes. So I'm going to talk about this 9 optimizer. So it's a new optimization algorithm that was found by interesting evolution program. So we look at this algorithm. Initially, we thought it's a randomly discovered algorithm. We didn't actually believe it makes sense. So we spent lots of time on that. Eventually, figure out that it's actually a quite interesting theoretical principle algorithm. It seems like it's doing something very intelligent. So tell a brief story about it. So I only have like 24 slides. So just slow me down with questions. Okay, so we want to solve optimization problems. And this is obviously one of the fundamental problems in training large AI models, right? And traditionally, we have been using stochastic gradient descent. We can augment it with momentum. This is widely used. And then we have adaptive algorithms such as Adam, AdaGrad, many other things. Nowadays, Adam W is pretty much the standard. Most of the default algorithm for training large language models. So you can almost think Adam W is the algorithm that attracts lots of powers, monies, and environmental costs by training these large models at data bases. But then there's a question of whether we can find better algorithms, because Adam W is relatively expensive. If we can actually squeeze out the performance, improve the algorithm even a little bit, it will amplify at a very large scale for all aspects: financial cost, time for training a model, accuracy, as well as energy efficiency and environmental sustainability. So this is a very quick recap of the standard algorithms. We have stochastic gradient descent, just update the gradient, or stochastic estimation gradient. And then we have momentum, which instead of updating the parameter with gradient, we update it with the exponential moving average of the gradient. Very, very simple. And then we have Adam W, or Adam, its variant Adam W. So what's happening here is that you keep track of both the exponential moving average of the gradient, as well as the gradient square. This is the element-wise square. And then you normalize the gradient, the first order momentum with second order momentum. Right? Optionally, you can apply a weight decay here, and that would actually correspond to so I need to turn this down. And that corresponds to adding a kind of regularization. Kind of regularization. This is actually important. So I think originally we had Adam, and people start to argue whether it's really better than momentum. And then I think after we have Adam W, it's pretty much the standard, and because this actually decay term actually improves quite a lot. But in terms of computational performance, Adam W tends to be better in most cases. But then cost-wise, Adam W is more expensive, obviously. And more importantly, it's memory more expensive, because you are going to need to keep track of both the momentum and second order momentum. And this is going to be huge. You basically need to keep track of 3 copies of model. At least 3 copies: the weights, momentum, and second order momentum. Versus if you just use momentum, you only need to keep track of one copy momentum, and then if you use SGD, then obviously it's even more, even better.
What is grad fxt squared?
Oh, element one square of the gradient.
Element one.
Yeah. Any questions? Okay, but then I think the problem is how can we find a better algorithms? Obviously, we have lots of experts in optimization here. We just spend our times and inventing better algorithms. But then that's another approach, which is resorting to a machine algorithm to discover new methods. And this is what has been tried by this group of researchers from Google and UCLA. So the idea is that they just set up an evolutionary program to search in the space of potential update rules. And eventually they find one algorithm they named as line that seems to perform well. So let me explain the idea. It's a very simple idea. Basically, think about Adam W or Adam. So in this case, you essentially can be characterized as a sum function that takes your current parameter, your gradient, your momentum, and your second order momentum, and return updated momentums as well as the parameter. Taking step size as a parameter as well. And then you just need to find this function. But this function is going to be some program. So some program like this. So we are going to just generate random programs and just try.
Where is this field getting into, right?
Yes. It's, yeah, I don't know. I mean, if they haven't tried this, I wouldn't believe this will work. But they might
I mean,
find
probably when people first started using this giant MLPs, they were like, what's going on?
Instead of having grad students randomly
Yeah,
checking.
exactly.
Might as well.
Yeah.
Might as well automate the pipeline. So we're like, oh, let's do momentum square and
Exactly.
time of momentum.
Yeah.
See what happens.
But this is much more efficient because
Yeah.
this guy can test lots of potential hypotheses and find out, right? Versus the student is not as efficient. So.
I don't know, Qiang Liu is pretty efficient.
Or vintage information. Okay, so this is what happens. So this is the master program. So they initialize the weights, they iterate, they have a learning scheduler. So they decide to put a separate learning scheduler. Learning scheduler is not them. And then they have calculate gradient, and then you have this train function, and then apply update. And this train function is what they are going to search. So they decide to initialize the program using Adam W. So they start from the program of Adam W. And then what they do is they are doing this evolutionary search. Essentially, they maintain a pool of potential programs, right? And then they rank the program and take the top percentage. And then they do some kind of mutation and then all kinds of other kind of things to generate new candidates and test them in iterate. The population search algorithm. And again, they come up a bunch of random programs. And this is one of the programs we
And they didn't ask GPT-4
they didn't
to look at this code because obviously
I-
someone's probably.
they have some, okay, so if you just generate a random program, the program may not be runnable, right? And sometimes you get equivalent programs. They actually have some program to actually check before they running the actual running the program, whether the sizes matches and many other things, right? Yeah. So this is actually one of the programs, successful programs we found. It's very messy. You can sort of see that lots of random numbers and lots of random functions. So the way they are doing this is like every time we just randomly generate a function and then randomly generate the input and output of the function, right? And every time they decide to either add a new statement or delete it or something else. And this program, if you clean it up, because many of these operators are redundant, it's not useful. If you clean up, you get something like this. And if you further clean it up.
May I ask what is Intel? Intel.
Oh, this is an interpolation. So you take a G and take a V, and this is a linear coefficient. Just take the linear combination, convex combination.
Also 0.8 times the first plus 1 minus 0.8 times the second.
Yeah, exactly, yeah. They have some like cosine or arcsine, which I don't think is useful at all, but they decided to add it.
No, but it's not cosine, it's hyperbolic.
Oh, cosine H.
Yeah.
They also have, I think, I saw some program, they actually found this, the sign, some.
Yeah, down there at the bottom.
Oh, yeah.
Sorry, is V968 equal to V minus V?
Yeah, this is one of the.
I don't know, the two lines above.
No, above, V968
So it's 0.
D
It
minus.
says, yeah, so if
Oh, yeah,
we
yeah,
are
yeah.
writing zero. Okay.
It's a redundant frame, so it will be removed. But they decide to keep this redundant statement.
No, but does that set V968 to 0?
Yeah,
Oh, okay.
of course. Yeah, so there are lots of redundant things, right?
I wouldn't say it's redundant, I would say it's.
No, it's
they're
redundant. It's not,
trivial.
it's not useful because you will, it's not functional.
Yeah.
useful. But they keep this redundant statement during the search.
Mhm.
Because you can mutate this guy. Yeah. Any questions?
So does the program also search over the different parameters?
They actually those are, these numbers are hyperbound. Yeah.
It's also discovered by the program.
Yeah. They will introduce some, they will either reuse this, they have a set of values, and they can either use these fixed values or they generate some random value.
No language model.
No language
It's,
model.
it's obvious that this will be done, it's gonna be done better with a language model, right?
Yes.
Yeah, so-
Potentially.
Of course, I mean, it's like you randomly, it's like instead of trying random stuff and not knowing how to code
Right.
versus trying random stuff and knowing how to code,
Yeah.
right? 99% of the time you're gonna do.
But
random
they
stuff that
already,
doesn't
they
even
they
comply.
already have this verification process that throw lots of nonsense programs away.
But
So-
I'm saying it's certainly clear to me that these ideas would be much more efficient if you were
Yeah.
feeding something that already knows how to code, like a language model.
Yes,
So
yes,
it's
definitely.
certainly, but they haven't done that yet.
They haven't done.
Okay.
Yeah.
Next week.
What are like the primitive functions that it's allowed to use in this process? Like, is it just print plus basic operations or something?
Oh, yeah, they have a candidate of functions they can use, but I think there are 50 or something functions they can use.
Anyway, this isn't the point of your talk, so.
Yeah, but I thought it's interesting.
But it works.
Okay, so, and then they further simplify the program, and this is what they get, and they name this algorithm as line for some reason.
It's a very, very bad idea.
And then they found this is better than Adam in their cases. Later, people tried it, and they find it's pretty much comparable, not always better, pretty much comparable. But the advantage is that this algorithm actually is more memory efficient than Adam. So this is like, if you write down the mathematician, this is actually the algorithm. You can see that you don't actually need to keep track of 2 copies of momentum, even though in the search space it was designed in such a way. And so you only need to keep track of 1 copy of momentum. That's more efficient. And then if you look at this function update closely, it has some, it's very similar to momentum, very similar to something that we are familiar with some, differences. First of all, they're using a sine function here, but that's a bit crazy because we would think if you apply a sine, you will lose information. It turns out actually using a sine is quite important. If you remove it, the performance will drop a lot. And then another feature is that if you are using a typical momentum algorithm, you're going to update your parameter with momentum. But they decide to update the parameter with the linear combination of momentum and the current gradient. So that's another feature they are having.
Isn't there like 1,000 papers learning to optimize?
Yes,
Do they compare against them?
these 1,000 papers doesn't actually work.
They don't? How did they get published?
So they are not generalizable in the sense that, so typically what has been done, like by of these original learning to optimize papers is that they set up this whole thing as a neural network, this
Yeah.
whole update, right?
Yeah, yeah.
And then I think then it's very difficult to generalize for some reason.
But these folks compared to all these other folks?
I don't think they compare because they only they only need to compare with Adam W, right?
Why?
Because that's the best.
No, but Adam W is a principal thing. It didn't need to compare with learning to optimize methods because it wasn't learning to optimize method. But this is, if it's, again, I don't know the literature, but I think that if you're going into, I'm doing data-driven optimization, specific tunings here, I would feel I need to compare to the data-driven optimizers. Whereas if I'm coming up with a new optimization algorithm.
No, this is not data-driven. This is the algorithm, right? It has nothing to do with.
Well, it's kind of data-driven, right? Because you're running a million versions of it and optimizing.
Oh, you're saying that whether it's better than these other methods that find. I think what they are doing is they are not. Okay, I don't really know.
But you see why it's data-driven, right? Because it's like, okay, I'm going to start them. I'm going to try a billion random stuff,
yeah.
and I'm going to test each one.
Yeah.
So therefore, I'm informing the algorithm by.
Yeah.
So it is data-driven.
It is data-driven.
Yeah.
But in the end, they don't care about how you found it. This is the final product they care about.
Okay.
Yeah. And now they are comparing this with the human design algorithms.
Okay.
So the competition is between human and.
Did they publish or they have?
Yeah,
Published?
they have published.
ICLR or?
I forgot.
Okay.
So how is this different from sine SGD with momentum? Like there's this.
Yeah. The difference is that, I will talk about the difference. Yeah. So the difference is using this combination and as well as using the weight decay. Yeah. So, yeah. But what I'm saying is that this is some familiar algorithm, but then it has some combination of elements. And then once you combine, it's unclear what they are doing exactly. So now if you actually unroll the update is pretty simple. What's happening is that you will do the exponential moving average as typical momentum algorithm, but then you have three features. One is the weight decay here, the sign here, and then you have an extra gradient here. The gradient is upweighted compared to a regular momentum. So the use of sign function, this is actually, if you look at literature, it's actually a very logical thing to do. This has, for example, sign SGD is actually distributing, taking the sign of the gradient. And you can also use the sign momentum, which usually take the momentum, the sign of momentum. And then it has nice interpretation when it's steep descent on the infinite norm. It's also mirror descent in some sense. And then you can also actually view as a kind of smoother version of SGD, sign SGD, because if you're just taking all these smoothing parameters to be zero, that they actually reduce to sign. So there has been papers arguing that the use of the sign, this normalizing the coordinate, is the key factor that explains the gap between SGD and Adam.
So, okay, so in sine momentum, like this weight decay parameter is included in the function itself, right? Or equivalently, you're minimizing
Right.
f of x plus lambda.
Right. Exactly, yeah. So this is something called a decoupled.
Like
rate,
an atom.
yeah. And then the use of this linear combination of the momentum and gradient is actually the idea from Nastro, if you look at closely. So if you remove the sign and the weight decay, you actually get this update, which is if you win some work, it's actually going to Nastro. So that's a nice idea. And then the intuition here, I think, is that because you are using sign, so you want to somehow stabilize the training. So if you add a gradient here, it will help stabilize the update in certain sense, because the momentum may not have enough information of the current gradient. And then as a result, they actually can use a larger momentum coefficient for the momentum, the beta 2. And that's actually helpful. Now another element is this decoupled weight decay. So the idea is that the weight decay is not applied on the gradient. if you apply the weight decay on the gradient, it's the standard L2 regularization. But they decided to apply the weight decay outside side. This actually is a key feature. And this is actually following the example of Adam W., which found that such decoupled weight decay is quite useful. Okay, so it does make sense. And while it has many aspects that looks reasonable, and then people already tested in many different cases and found it actually works. So the question is whether it's truly a theoretically correct algorithm, or it's a kind of buggy algorithm that happens to work, right? This was the question. And then we thought about this problem. We didn't think it makes sense in the beginning. We tried to fix it. But then later we found it's actually a brilliant algorithm. So if someone actually worked out this algorithm, I would think he's really brilliant. Okay, it turns out this guy, this update, is actually a principal way to solve this this constraint optimization problem. So it minimizes the loss function, but subject to the constraint that the maximum absolute value of the weights is small or equal to 1 over lambda. So this is due to the use of weight decay, right? And then we tested and find that this constraint is enforced really well. So this is one of the neural network that we trained, and just
Why do you get an infinity norm there instead of like a 2 norm or something?
that's because you have a sign.
Is it because of the sign?
Yeah, it's because of the sign.
I see.
Yeah, I will explain why. You can actually replace this with any norm.
Oh,
But if I replace with any norm, it's different, bro. I mean, this is convex, right? So
Yeah.
you say every coordinate is small.
Yes, every coordinate has to be smaller than this bound.
Yeah.
So we actually plotted, you can sort of say that in the beginning, we initialize some Gaussian parameter. This is the histogram of the weights. And then within 250 steps, 200 steps around, it's actually squeezed into this interval, which is defined by 1 over lambda. So this constraint is enforced really well. Any question?
Like intuitively, why is this helpful?
Okay, so what do you mean by, there are two questions, why this is true, and then.
Yeah, true is not clear, but
Yeah.
like even like, let's assume that this is true, but why is this helpful? Like,
I don't really know, but one explanation is that if you set the lambda properly, such that the true solution is included in this set, then it's like enforcing a prior. It tells you that if I'm violating this constraint, I will really push my solution really, really fast to that region. And then once you enter the region, you will search for your algorithm, for your solution. So it imposes a prior.
but so does any norm.
Yeah,
Yeah, so does any regular.
Any norm.
Any norm.
yeah, but this is a constraint.
Yeah.
It's
No,
a,
but why does the infinity norm impose a stronger prior than the 2 norm?
I don't know. I don't know. I don't know why this is better. I can only explain that.
By the way, a remark here, in adversarial attacks, you are given an X, and depending on what threat model you have, one of the most common threat models is the L infinity threat model. So you're allowed to perturb X with exactly this constraint.
Exactly.
And exactly this algorithm is called the fast gradient sign attack.
That's different, actually.
Well, there is no momentum classically, but it's the sign of the gradient, right?
Yeah, the
So-
sign of the gradient,
Yeah,
yes.
so this is a momentum fast gradients FGSM. with
It's a variant of momentum.
Yeah.
Yeah.
So I don't know if in adversarial attacks people did a GSM with momentum, they probably have.
Yes.
But yeah, this is a very, very used technique to enforce a constraint in X. This is widely used in attacks, right?
Yes.
Yeah.
It does have, I think what's happening is that it combines all these elements that is known, right? But the combination of these 3 elements is unique.
Yeah, it works, yeah.
Okay, so now why, intuitively, why this is true? Well, because if you look at the update rule, it's actually the sign of something, UT, which is the whole thing, minus lambda xt, right? So now if I'm not satisfying this constraint, then the magnitude of x lambda xt is going to be larger than 1. So then, and the sign part is always has a magnitude 1, right? So then if this is very large, then the whole update is going to be dominated by the rate decay. So the rate decay is going to decrease xt until this whole thing is small or equal to 1. Then you'll start to get something interesting because these two will start to balance and you will try to actually solve the optimization. And when this is large, it will basically just try to enforce the constraint. So you can sort of see that this algorithm will find this constraint very quickly and then search inside the region for the optimal solution.
It will also always click the, so it always updates using plus or minus y. It
Yeah.
never, but I guess it uses the magnitude of the gradient and the momentum.
They don't use the magnitude of the.
It is, right?
Well, but it's irrelevant, meaning that if you scale your gradient with any number, you will get exactly the same result. So this is actually a feature of this.
So if I scale the gradients here, this algorithm is invariant now?
It's invariant, right? Because if you scale all the gradient, the M momentum is also scaled. Let's see, if you multiply the gradient by 100, you will also multiply the momentum by 100.
But that will change the evolution, no?
It doesn't change because you are taking the sign.
Okay, all right, because
Yeah.
both terms will be multiplied by.
But you can get a similar effect by just normalizing it, like Adam does, by normalizing.
Adam is not exactly invariant because you have this epsilon, but you're right, yeah, almost.
So I'm not familiar with this kind of like context because I don't do neural network training much. I'm doing PD constraint optimization. And so my question is that if you replace the L infinity norm here by L2 norm,
Right.
and you repeat it like every like arguments here, can you recover the same like in standard gradient descent?
Yeah, you are recovered, yes. I will talk about that, yeah. You can replace this with any convex function.
But
Well, it would be very different.
Yeah, but I will talk about it.
so despite of that, there's still like advantage, like just a line that using the sign function can get you.
So it seems like the use of sign function is very important, but my theory doesn't explain that. So I don't know why sign is
So
better.
it's still, people are still like exploring that.
Well,
why it's-
people intuitively know that you want to normalize the magnitude of every coordinate in neural network training because all this adaptive algorithm is doing something like that. Well, we have the explanations, we have papers discussing that, but I don't have the intuition. I don't have, I don't understand. Yeah. Okay, so now here, this intuition only explains that this whole thing will enforce the constraint, but it doesn't explain why actually solve the optimization when the constraint is satisfied. So in order to do that, I'm using this Lyapunov method. The idea is that I'm going to find a Lyapunov function and show that the algorithm actually monotonically decrease that function, and then show that the minimum of that function is actually solving the problem that I care about. So here's an example of using the Lyapunov function. Let's just take the standard momentum algorithm. This is also called heavy ball algorithm, because if you take the zero step size limit, you get this differential equation that is a ball that is traveling in a potential field with some damping fluctuations, right? And then you can actually calculate this energy function of this whole system. The energy function is the potential function plus a kinetic energy. The kinetic energy is really just the magnitude of your velocity, which is momentum ampere, right? And then you can show that this energy function is decreasing monotonically. And then further, you can show that minimizing this function is equivalent to minimizing the F. So this actually justifies the optimality of the simple momentum algorithm. So I'm going to use
Why
some.
is the potential energy fx and not grad?
Oh, no, this is the energy function, potential function. So
Yeah.
you take the gradient and you get this, right? What do you mean?
I mean, why isn't the potential energy the gradient, not the fx itself?
No, the energy is the. Oh, okay, so you have a potential energy, you take the gradient, you get the force field.
Yeah.
Yeah. Yeah.
Oh, I-
Yeah, so the energy is a numerical number, but if you take the gradient, you get the force.
So say if I take the gradient of the Hamiltonian,
Right,
I get force.
yes,
Okay, I should know physics, yes.
yes,
Okay.
yes. Let me see. So, yes, I think the nice thing about this is that this momentum algorithm is non-monotonic, right?
In what?
In F, it will actually oscillate. So,
Oh, you say I will make steps that increase my objective.
yeah, yes.
Uh-huh.
So if you analyze the gradient descent, you will say, okay, I'm going to just calculate my updated fx and see monotonic decreases. But this actually doesn't apply to momentum.
Mhm.
So fundamentally, even if you use infinite small step size, which will reduce to this ODE system, the
Yeah,
F doesn't.
and that's the ideal moment, right? Because you're like, oh, I have this ball, it's rolling down, it
Yeah.
has to go up a little bit to
Yes,
get to the
exactly.
deeper well, right? So
Exactly.
it's fundamentally,
Yeah,
it's a feature, not the bug.
It's a fundamental feature of that. So
Yeah.
this is a fundamentally non-monotonic algorithm.
Yeah.
You cannot certify the convergence of system by just looking at the app. But then it turns out if you add this kinetic energy, then you get this total energy that is monotonically decreased by the system, right? This is the intriguing part of this.
So this does become monotonic.
This becomes
In a
monotonic
strange,
in terms of H.
I can, any algorithm you give me, I can come up with some random thing that it's monotonically minimizing it, right? So that's my counterpoint to this argument.
No, not really, because only algorithm that converge has its Lyapunov function to satisfy. If you
Okay,
if you
so
have
strictly decreasing, you're absolutely right. If I could find a strictly decreasing function, I can use it as an argument to prove
to prove, yeah,
convergence,
exactly.
therefore, yes.
Yeah,
But
exactly.
the fact that there exists such a function is a trivial statement because I can always come up with a function for any algorithm.
That converges.
Yes.
That converges.
Yes.
Yeah. Questions? How much time do I have? Oh, okay, I need to speed up. Okay, so then what I'm doing, I'm going to use this approach to prove it for line. I'm going to do a generalization first. So first I'm going to take any convex function, and then I'm going to replace the sign with the subgradient of the function, convex function. So if I'm taking the kappa here to be the L1 norm, I will get the sign if I take the subgradient. Right? And now that I get a more general algorithm. It turns out this algorithm is solving this guy. It's a regularization of F with this conjugate function of kappa, right? And then when does it actually reduce to a constraint optimization? Well, sometimes if you calculate the conjugate of convex function, you will get infinite values. And that's when you need this problem reduces to a constraint optimization that enforces the constraint that the X has to belong to the domain of K star, where this K domain is defined as the set of values where K star has finite values.
K star is a set, right?
K star domain K star is a set, but K star is a function.
A vector?
It's a number of function. It's a
It's a
scale value.
Oh.
It's the conjugate function.
Oh, okay.
Yeah, it's a conjugate function of kappa. Kappa is a convex function.
Like a dual.
It's a dual.
Yeah. So this is the example where kappa is L1 norm, then the conjugate of kappa is actually this indicator function which takes 0 if the norm is smaller than 1, and otherwise infinite. Because of infinite, it reduced to a constraint optimization. Right. And turns out this family of line king, so I choose the kappa to have the I've actually generalized lots of algorithms, mirror descent, all kinds of other things. Frank Wolf, if you work out, you will find the correspondence of this thing. It also actually induces a family of new algorithms. If you choose some strange choice of kappas.
Oh, but Frank Wolf, for example, takes any polytope, right? Whereas here this algorithm cannot generalize Frank Wolf because Frank Wolf could work on any polytope, right? Can this?
This actually generalized because it works for any K. Frank Wolf takes any K.
Oh, okay.
Yeah.
So your Lion King takes any K. Okay.
Yeah, it takes any K.
Alright.
So that actually strictly generalized language. Yeah. Well, yeah, it's very general, I would say, but we tried this, all these versions. We didn't actually find it's useful for now. So we'll focus on line for now. Okay, so then, and then what's the property of this? Well, we actually take the ODE version of this for simplicity. And then we find that this system actually has two phases. In the phase one, if the constraint is not satisfied, then it's going to decrease the distance of your solution to that constraint set exponentially fast. And this distance is any distance that satisfies triangle inequality. So it's a very fast, rapid enforcing of the constraint in the first phase. And in the second phase, which is the difficult part, it turns out in the second phase, it minimizes this Hamiltonian function. So roughly speaking, you can sort of see this is the potential function. This is the objective function we are minimizing. Now, this is a kind of kinetic energy. It's a generalized kinetic energy. And the way to see it is that we have this Young inequality, which says that the sum of conjugate and the original convex function is always larger than this inner product. So this whole energy is always larger equal to 0. And also for any x, you can find the solution of m that make this guy 0. So if you minimize this whole thing with respect to x and m, you will get a minimum point of x if you get rid of m. So minimizing these two are equivalent. But then we show that this ODE is actually monotonely decreasing this function. So it actually solve the problem over here.
So phase two is when you are inside this constraints.
Yes, yeah. And once you are inside, you wouldn't go out.
Oh, okay.
Because that distance decays exponentially.
I have a question. So for something to be a kinetic energy, you said that just for my physics.
It's a metaphor. It doesn't have to be.
Yeah, I just want to know, to call something an energy, the requirement is it has to be greater or equal to 0.
No requirement.
Oh.
It's just a metaphor.
Or you're just calling it.
Yeah, just for energy.
I'm just saying something has to satisfy some properties in order.
I don't think so.
Okay.
I mean, energy is something that decreasing physically. Okay, so and then you have for the discrete time case, you can also derive parallel results. So the distance decrease monotonically, and then you also have another Lyapunov function, a variant of that is decreasing monotonically if the step size is sufficiently small. Okay. So this is the main result, but any questions?
What is delta T?
This is actually some positive number. It's complicated, so I didn't write the definition. Okay, so now here's the proof. It's actually very tedious to find that Lyapunov function. And it's very tricky to prove. But then after some work, here's a very simple intuition.
Sorry, what are you proving?
I'm going to prove this thing is monotonically decreased by the ODE system.
Okay.
So
I'm saying this.
So this Hamiltonian that you made up is
yeah,
going to be decreased by
yeah.
by the dynamics of this ODE.
But it's not gradient descent.
It's not a gradient descent. It's not even a gradient flow.
Okay,
But still it will decrease.
in every step.
In average step. So now I just want to explain how is it possible for a non-gradient flow to decrease a function monotonically? There are several reasons. There are several structures that enables this, but the structure that enables this particular monotonic descent seems to be a new structure that cannot be explained using previous approaches. But I'm going to explain that structure now. Does that make sense? Okay, so the structure, the idea is the following. So now I'm just abstract away the details. Just assume I have some arbitrary ODE system, and I have some arbitrary function. So I want to calculate the decreasing rate of that function. So then it's the inner product between this update function with the partial derivatives of the Hamiltonian function, right? Now, in what case this guy would be small equal to 0 is the question, right? So here's one scenario that this can happen, which is if you can somehow show that the partial derivative of h with respect to m equal to this guy, or this u hat of v hat is some monotonic transform of v and u. So the inner part of v hat, so v hat is a function that you need to construct, right? But it has to satisfy that inner part of v is always larger than 0. And u and u hat inner part are always larger than 1. So there are monotonic transforms in u and v. So now if I construct the u hat and v hat such that this equation holds, then this Hamiltonian is monotonic decreasing because it's actually a simple calculus. If you just pipe this guy into here, this guy into here, you get this whole thing, right? But then if you look at closely, what's happening is that you have this u hat and ut, v hat of vt, which is always positive. So that's nice, you get this. And then you have this u times v and v times u. It's a crossing term, which you can never guarantee positive or negative, but then they are canceled. Right. So then this whole system is decreasing. Right. This is the idea.
In the context of your like the algorithm, what is v hat?
It's some complicated function that I don't think I remember now. It's a yes. And you have to use some inequality from convex function to show that this is true. Yeah. Any questions? Okay. That's it. That's what I want to talk about. But I think it's an interesting experiment to analyze an algorithm in which random is. Initially, we didn't think it makes sense, but later we realized it's actually quite interesting. I think there are some potential directions. One is that I think now I kind of believe that random search algorithm does have potential, lots of potential. That if you think about language models, right, it's another case where you have this algorithm found model that seems to have reasoning capacity, right? So I think maybe some kind of improvement of the search algorithm, maybe incorporating language models or some other strategies could improve the method. And it would be a very good investment because once we find a better algorithm, it will save computation for all the future computation. Right? Another direction is that now that we know this algorithm is theoretically principled, we can apply explore all kinds of improvement and extensions of that. And one of the recent work, we have something that aligns line to enable communication efficient algorithm, where we only need to communicate the signed updates. So you will only require binary communication rather than real value. That's it. Thank you. Any questions?
Yeah, so I read when I looked up, it was a New Lips 23 paper, the Lion thing, and they say they used it. Mosaic ML uses Lion as the optimizer for training the Databricks language models now, and they also said that the MPT7B
Exactly.
used. So I guess then my question is, given that this algorithm needs only a sign per coordinate,
Right.
Which I guess they're doing it for the weight, right? So you need a sign per weight, right?
Yes.
Is there a trick to do it much faster than not computing? For example, is that the benefit that they're already using, for example? Or could there be a benefit here that you don't need to have full backpropagation? Or maybe you can just have a very quick test for 80% of the coordinates. I can just tell you if it's +1 or -1 without the full backprop.
Yeah.
And hence be able to compute this much faster. Is that something that people are exploring already? Or
I think it's a very interesting direction. People are not doing that yet. Yeah, I think I think right now you have to compute the exact gradient momentum, right? But as you
But I'm gonna
said,
just compute a few coordinates
Yeah,
and they say,
yeah,
you know,
it's
it's like 57, it's probably going to be plus one.
yeah, it's possible. It's definitely possible, I think. But it's so recent that people haven't explored it. Many people don't even know this algorithm, so it will take some time.
Yes.
But in the distributed line algorithm I mentioned, we actually leverage the sign to develop the communication efficient algorithm. Because now, you have each machine that calculates this sign update, and then you only communicate the sign update between the machines, and that's actually helpful.
The
compared-
distributed issue is also interesting.
yeah.
And you also need, it's more expensive because you need to keep the previous step of the model. If I understand correctly, there is some aspect that is more expensive than gradient descent.
It's more expensive than gradient descent, but not more expensive than momentum.
Right.
Because you only need to keep track of M. So
Yeah.
the actual computation is only this, because you will calculate gradient anyways, the actual computation is really just linear computation, which is small.
M is as big as the model, right? So
Yes.
if I have a 7B model,
Yes,
I need to keep 7B for M and 7B for X.
yes, but that's the only, but if you do momentum, you also need to have the same thing.
Yeah.
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 Any other questions? Otherwise, we can take off, I guess. Okay. Sounds good.
Maybe